All right, section 2.4, we are going to be modeling with quadratic functions. Up until this point, the book has given us an equation, and from that equation, we've determined the vertex, whether it opens up or down, the size and shape, and made predictions from that, given the equation. In this section, we're actually going to be writing those equations. So we're going to be given information about the parabola, and from that, we will come up with that equation. Okay, so based on the information you're given, there's really going to be three different ways we're going to do our problem. Okay, so the first way is if we're given a point and the vertex. The important problem part here is you have to know that vertex. The vertex is going to be the point HK. Okay, so those are just the variables we tend to use for a vertex. And you need one other point. You need some other point here for you to determine whether that opens up or down and how wide or narrow that parabola is. So if you're given the vertex, we're going to use something called vertex form. Okay. Vertex form basically takes the standard. We know our parent function is y equals x squared. And we know this parabola has a vertex at 0, 0. Okay. So what the vertex form does is it shows us how we shift left, right, and up and down. So we know, okay, from our transformation section, okay, that we can take this function, and if I shift it left or right, it's going to be inside the function. So we're going to write it x minus h here, squared. So this minus h, again, is going to shift it left and right. The negative, again, just denotes that left and right shifting works backwards. Okay. Okay, so that's going to be our x minus h, and then we're going to move it up or down, plus k. So that plus k is going to move it up and down. So what that's going to do is it's going to take our normal vertex of 0, 0, 0, and it's going to move it to be the point hk, hence our vertex hk. Just because I have our shift left and right in here is going to translate into the x coordinate of my vertex, and the shift up and down is going to be the y coordinate of my vertex. But then we also could possibly have a stretch or shrink, so we're going to multiply out in front by an a. There could be some constant out there that's going to stretch or shrink it. Okay, so this is what we call vertex form, and if we know the vertex of the parabola, this is what we're going to use. So down here in example 1, okay, here we have a graph over here. Okay, and in this explanation, the graph shows the parabolic, just parabola path of a performer who is shot out of a cannon, where y is the height in feet. So here this y is how high up and down it is. And x is the horizontal distance traveled in feet. So how far over left and right it goes. Okay, so here I can tell from this graph when it's left and right 0, it's up 15. We want to write an equation of the parabola. The performer lands in a net 90 feet from the cannon. What is the height of the net? Okay, so we'll get to that part later. First, let's just focus on writing the equation for the parabola. Okay, so to write the equation for this parabola, we are going to have to notice, first of all, they give us the vertex. There it is, right there. There's my vertex. Okay, so there's my vertex. So there's my h, and there's my k. Okay, so I'm going to go ahead and at first I'm just going to write vertex form. Y equals a, there's our stretch and shrink, x minus h squared plus k. Okay. All right, so a, x minus h squared plus k. My h and my k is how far over. So this, my original parabola, of course, is going to have a vertex of 0, 0 over here. So this is shifting 50 to the right and 35 up. So that's going to be 50 to the right is going to translate to that, and 35 up is going to be my k. So we'll have a x minus 50 squared plus 35. So that's going to give me a parabola with the vertex of 50, 35. Again, we need this minus in here showing that, I guess that works backwards. We're shifting to the right 50. Okay. The only thing we're missing is this stretch or shrink. We don't know. We don't know that this a right there. So now we need to find a. So over here, I'm going to say we need to find a. To find a, we're going to use the only other bit of information they give us, this point. They give us the point 0, 15, which tells me that when x is 0, y is 15. That's one possible ordered pair. There are many different ordered pairs. I just need one of them. I know one of them. I know when x is 0, y is 15. So I'm going to plug that in for this x and this y. So y is 15, x is 0. Okay. So then we'd have 15 equals a times negative 50 squared is 2,500. Okay. And then we're going to, let's see, subtract the 35 from both sides. So we've got negative 20 equals 2,500 times a. Divide both sides by the 2,500. So a is equal to, I'm going to type in, I'm grabbing my calculator, type in negative 20 divided by 2,500. And we get, I want it as a fraction, negative 1 over 125. So there's my a. So I can now plug that in over here for a and write my equation. X minus 50 squared plus 35. So there's my equation. So we got that part done. Next, it says, the performer lands in a net 90 feet from the cannon. What is the height of the net? So we're landing 90 feet away from the cannon. So it looks like we're landing over here, right there, that point. And we're over here at an x of 90. We want to find the height. Well, the height is going to correspond to this y value. But this is my x when x is 90. So basically what I'm trying to find out here is when x is 90, what's y? So to find that, I'm just going to plug a 90 in for my x. So I'm going to go ahead and I'm going to do this using Desmos. Okay. So we have y. Oh, wait, let's just get rid of the y. So let's go negative 1 over 125. We're going to need parentheses. X is 90 minus 50 squared. And then we're going to add, add 35. Okay, so it looks like when we plug that in, we get 22.2 feet. So when we plug that in, we get 22.2 feet. So there is the height of the net, 22.2 feet. Okay, all right, next. Okay, so that's if you're given a point and a vertex. Second, what if you've given a point and x-intercepts? Okay, so we're given where it crosses the x-axis. Again, remember that's what x-intercepts mean, where it crosses the x-axis. So we're going to use that, what we call intercept form. Okay, so we're going to use intercept form, which y equals a x minus p x minus q, where q and p and q are those intercepts. Okay. Again, remember this is all multiplied. This is a times x minus p times x minus q. So this is intercept form. Okay, so here in example 2, we're going to have intercept form. So here we have a meteorologist creates a parabola to predict the temperature tomorrow, where x is the number of hours after midnight. So x is the number of hours after midnight. Okay, so there's 3 hours after midnight. Looks like we're counting by threes. And y is the temperature in degrees Celsius. We want to write a function that models the temperature over time and then find out what is the coldest temp. So we want to first of all create a model for this. So we know our intercepts. Our intercepts over here are right here and right there. So at 4 and over there at 24. So one of them would be P and one of them would be Q. It doesn't matter which one. So let's go ahead and let's write intercept form down. Y equals a x minus p x minus q. Okay, so we know my p and my q. X minus 4, parenthesis x minus 24. Okay, so basically we're done, except for, again, like the last time, we need to find a. Okay, so in like our last problem, we need to find a. So that's again where that other point comes in handy. So they give us this other point, 0 and 9.6. So we need to go ahead and we need to find that a by plugging in that 0 for my x's and 9.6 for my y's. So 9.6 is y, a, 0 minus 4, 0 minus 24. So we get 9.6 equals a times negative 4 times negative 24. Okay, so negative 4 times negative 24 is 96. Divide both sides by 96. A is 1/10. Okay, so then we know my A. So there's my equation. Okay, and I guess I should have noted in the last one, we can always check our work on these by looking at the graph. Okay, so I'm going to go ahead and I'm going to look at the graph using my calculator, but you can also do it using Desmos. Okay, so here it was 1/10. I should probably put that parentheses. X minus 4 parenthesis, X minus 24. And then we look at the graph. Oh, my window's really funny. So let's go window. Let's go back and let's look at our graph here and see what would be a good window. Here it looks like my X's go from 0 to, I don't know, about 30. So, and then, so we'll go 0 to, oh, sorry, wrong one. So with my X's, so in my window here, my X min, we're going to go 0. X max, we're going to go up to 30, and we'll count by 3s because that's what the graph does. My Y's there went from negative 20 to 20. So there's Y minimum, Y maximum. And then what do we want to count by my Y's on? I don't know. We can count those by 5s maybe. And then look at the graph. So there it is. And then we want to find, it says, what's the minimum temperature? So what is this lowest point here? So we're going to go ahead, we're going to trace. And we're going to look for, we're looking here at my Y's to figure out where does it get the lowest. So it looks like, oh, it was somewhere in there. Negative 9.999, negative 9, somewhere around maybe 14. Oh, yep. At 14, we actually hit negative 10. Okay. So it says, what is the coldest temperature? Whether over here at 14 hours, we reached a negative 10. So negative 10 degrees Celsius. Okay. So now what is the average rate of change in temperature over the interval in which the temperature is decreasing and increasing? So let's go ahead and let's look over here at our graph. Okay. So if we look at our graph, we want to know what is the rate of change, average rate of change. So for that average rate of change idea, average rate of change, whenever I see that average rate of change, I think slope. I'm looking at the slope between those 2 points. If we remember, slope is the change in Y over the change in X. So I want to look when my temperature is decreasing. Well, my temperature is decreasing from here to here. And we know from the previous, this lowest point here is the point 14, negative 10. So we want to find the slope on that interval for that orange bit where we're going down. So my slope, my rate of change for the decreasing part is going to be my change in Y over change in X. So I subtract my Y's, 9.6, subtract a negative 10. And now I'm going to subtract my X's, 0 minus 14. 9.6 minus negative 10 is positive 19.6 over negative 14, which is equal to 19.6 divided by negative 14. We get negative 1.4. Okay, and that's going to be degrees Celsius per hour because it's a rate. Okay, and this here was temperature and this here was hours. This was degrees Celsius, this was hours. So it's degrees Celsius per hour. So that's why where it's decreasing. So now we want to go and look where it's increasing from here to there, that little bit. So again, we're going to use this same change in Y over change in X for the increasing part. So we're going to subtract the Y's. So I'm going to take negative 10 and subtract 0. And then 14, subtract 24. So we'd get negative 10 over, negative 10, which gives me a positive 1. Again, degrees Celsius per hour. So there's where it's increasing. Here's where it's decreasing. It says compare the average rate of change. Well, so comparing these two, it actually decreases faster. By looking at this, this is a bigger negative number than this one is. So it actually decreases faster than it increases. So we would say decreases faster than it increases. Okay. All right, next. Okay, so now we're going to go ahead and we're going to look at data and determine, okay, can I tell just from looking at a table or given information about a data set whether it's going to be quadratic or not, or quadratic would be a good fit? Okay, if you remember from the linear section, when data has equally spaced inputs, meaning it goes up by the same amount each time, like here, each one of these goes up by 1. Then you can actually look at the differences or the subtractions between these outputs and determine whether this guy is going to be quadratic or not. Okay. We could determine whether it was going to be linear, if you remember back on the linear section, if those first differences were all the same. So we would go ahead and we would find these first differences. We would subtract. The 4 minus 9 is negative 5. 1 minus 4 is negative 3. That'd be negative 1. That'd be 1, 3, and 5. So these here are the first differences. If these were all the same, then we know it would be linear. A line would fit this data, but they're not all the same. So we have to go and subtract one more time. So we're going to subtract. Negative 3 minus a negative 5 is 2. Subtract here, we get 2. Subtract here, we get 2. These all are the same. These are the second differences. And if the second differences are all the same, then it's quadratic. It's going to exactly fit a quadratic function. Okay, so if the second differences are the same, it's quadratic. Okay, so here we have a table of values that NASA has created a weightless environment by flying a plane in a parabolic path. The table shows the height in feet of the plane, t seconds. So it looks like here my input is t, my output is h. Okay, and if you notice, my inputs go up by the same amount each time, up by 5. So it says, write and evaluate a function to approximate the height at which this occurs. So first let's determine, will a quadratic function fit this? So let's go ahead and let's look at the first differences. So if I subtract these two, I get 2125. If I subtract these two, we get 1575. So it looks as if first differences aren't going to work. 475 is these two is negative 75, and these two is negative 625. So it looks like first differences don't work. So let's go ahead and let's do second differences, just to double check. Subtract these two, we get negative 550. Subtract these two, negative 550. These two, negative 550. Okay, so it looks like second differences are working. So the second differences work. So that tells me that this is quadratic. Okay, I do not know the vertex. Okay, first of all, I do not know the vertex. Don't know it. I do not know any of the intercepts. Don't know it. So we are down to this last one if I'm given 3 points. 3. If we are given 3 points, there's a way you can do it without your calculator, but we're going to use our calculator. Use a quadratic regression in the calculator. Okay, so I need to then use a quadratic regression in the calculator. Okay, so first I'm going to need to put, if you remember from our previous section, I have to go to Stat, Edit, and put these into List 1 and List 2. So I need to Stat, Edit, and put these into List 1 and List 2. So I'm going to go ahead and I'm going to do that. Okay, let's go ahead, let's zoom in. Okay, y equals, oh no, sorry, Stat, Edit, hit Enter, and then List 1, List 2. I'm going to arrow up, hit Clear, arrow down to get rid of this stuff that I have in there. Oh. I don't know what I did. Okay. All right. So now I need to put this data set in. Okay. So we've got 10. So I'm going to put all my X's in. Okay. And now I'm going to put my Y's in List 2. All right, so I have them in. Now if I want to look at them, Okay, I would go to the easiest way to do that, go to my y equals, delete what's ever in there, arrow up and turn my plot on. Okay, but now I'm going to have to adjust my window because I'm not going to see my points. We look at our table. So we'd go back, look at the table. My x's or t's here, 10 to 40-ish. So we'll go 0 to 50 maybe. Okay, so we'll go ahead and we'll come in and we'll go 0 to 50. So 0 to 50, I don't know, we can count by 5s or 10s. 5s. My y's, though, are super big, like 26,000 up to about 30-some thousand. So how about we go 20,000 to 40,000? And let's count by 10,000s there. And then let's go graph. All right, there's my points. Those do look quite quadratic. They make a nice little parabola there. Okay, so to go ahead and determine, to actually get that parabola, I'm going to have to go to stat. And now I need to calculate. And from before, we did a linear regression, but we don't want a linear one here. We want a quadratic. So we want to come down here to option 5, quadratic regression. List 1, list 2. And then I want to store this in my y equals. So again, we hit vars, over to y vars, function y1, and then calculate. So there's my equation. My equation, y equals negative 11x squared plus 700x plus 21,000. And if you notice there, my r value is 1, which tells me it fits perfectly, that r squared value. So to get our regression, we went to stat, calculate, quadratic regression. Okay, and then we went vars, y vars, okay, function to get y1. So then our equation, we would write it down, y equals negative 11x squared plus 700x plus 21,000. So there's our equation. And it says, write and evaluate a function to approximate the height at which this occurs. So what occurs? Let's go back and read. After about 20.8 seconds, so that's when time is 20.8 seconds. Oh, we got to switch our variables up. If you notice here, they use a t for x and an h for y. So I need to write this equation that way. So we use that one instead. But now when t is 20.8, excuse me, what is h? Is what we're trying to find. What is the height? So when time is 20.8. So we already have that in our calculator. Let's go ahead, let's just use it. So we already have that in our y equals. See, there it is. And we can graph it. There it is. So we want t, or my x, to be 20.8. So I can just hit trace. There I'm tracing my plots. I'm going to need to arrow down to get to my y1 and type in 20.8 equals. Look at that. 30,800.96 feet. So 30,800.96, and that is in feet. So at that height, we would experience weightlessness. Okay, so this was somewhat real life data, except I think the numbers were fudged a little to get it to have this perfect second difference. Real life data doesn't really work that way. We don't always get that perfect second difference. So we can use our calculator and use that r value to determine how well it fits. So we use, in this case, for a quadratic, we use an r2 value. Again, we want it to be close to 1. That r2 value will never be -1, but close to 1. The closer it is to 1, the better the fit. Okay, I don't think I'm going to do example 4 just for time. Really, it's the same thing. We're going to put this in our stat. We would stat, edit, and do a quadratic regression on this. Okay, we end up getting an R value that's not exactly, if you were to do it, not exactly 1. It ends up being like 0.999 something. So it's not exactly quadratic, but it's pretty close. Okay, but yeah. So if you have any questions, please come see me, and good luck on your practice.